Hey guys, this is the first video for section 6.4, which is on the fundamental theorem of calculus. So remember from last unit, the first derivative test, second derivative test, information about concavity, those make up about 10% of the AP exam. The fundamental theorem of calculus makes up about 15% of the AP exam. So we're going to spend a good chunk of time on this, like we did with that last set of information. It is the, fundamental theorem of calculus. And with a name like that, kind of important, kind of a big deal. So what we'll learn about in this section is, and we're going to split this up into a few different videos in a few different days. And sometimes I don't print this slide, but I like this one because I like the and why. The fundamental theorem of calculus is a triumph of mathematical discovery and the key to solving many problems. So it's a big deal. When Newton and Leibniz discovered the relationship between derivatives and integrals, they made connections there that, have been able to lead people to solve problems that were previously unsolvable. So there's two parts to the fundamental theorem of calculus. And the first part is the derivative of an integral. And so I actually think, and I don't know why my integral signs don't copy over here. So that's strange, but on your own paper they should look like that. The second of these two, so that this is kind of the way it's worded, kind of officially. Fundamental theorem isn't something that typically needs the same sort of justification as our other main theorems. So let's review those real quick. We've got IVT, we've got MVT, we've got EVT, and then we've got this one, which is the FTC. So lots of times with these guys, we have to justify like our function is continuous and it's on a closed interval or it's on an open interval or it has to be differentiable. But for fundamental theorem of calculus, questions aren't typically asked that way. So I think the more useful form of the first part of this fundamental theorem is this one. So basically it says if you take the derivative of the integral from a to x, a here is representing a constant, of f of t dt, so t here is our variable within the integral, then that equals f of x. So I'll show you some examples of what this looks like, but these three things are kind of the important parts of what to remember about the fundamental theorem, at least this part of the fundamental theorem. Every continuous function is the derivative of some other function. Every continuous function has an antiderivative. And I think the big one here is the process of integration and differentiation are inverses of each other. So like addition and subtraction, multiplication and division. When we integrate and when we differentiate, we're undoing itself. So that's why when we take the derivative of an integral, we end up with just the function we started with. Now we do have a variable change and we'll kind of talk about like what's going on there. But that's kind of an important part of the fundamental theorem. All right, so we'll jump right into example 1 here, applying the fundamental theorem. So we've been asked to find the derivative of the integral from pi to x of sine of t dt with respect to x. And according to the fundamental theorem, the way we're applying it, basically if you take the integral from a constant to x of a function in terms of t, the answer is the function in terms of x. So the answer to this question, it's very simple, it's very straightforward. Our function is sine of t. That function in terms of x would be the sine of x, and that's it. Basically, you're just substituting the upper limit of integration in for the variable t. Now, just so you kind of get an idea of why that is, let's kind of take this step by step. We're going to evaluate the integral first. So I'm just going to write this derivative out in front. When we evaluate an integral, we do that by finding the antiderivative of the sine of t. So the sine of t's antiderivative is negative cosine of t. Okay, and I know that because if I take the derivative of cosine of t, it would be negative sine, and so I need the negative here, so that it becomes positive sine. And I'm going to evaluate that from pi to x. Okay, I'm not going to do the derivative yet. I'm going to go ahead and do the evaluation part, which means for the I plug in the upper limit of integration, which is negative cosine of x, minus, and then I plug in the lower limit of integration, which is pi, and then I'm going to keep evaluating that. I haven't taken the derivative yet. So I got all kinds of negatives going on here. The cosine of pi is negative 1 times the negative that's already there becomes positive 1. Okay, so then that ends up being the negative cosine of x minus 1. Now let's take the derivative of that. Well, the derivative of negative cosine is sine. And the derivative of negative 1 is 0 because negative 1 is a constant. And so my answer here is just sine of x. And so that's what this part of the fundamental theorem of calculus is saying. They're inverses. They undo each other. So the derivative and the integral undo each other, and then we have that variable change from t to x because that's how we do that kind of antiderivatives. And then when we do the antiderivative and evaluate, we put the x in, and then we take the derivative and we end up back to where we started. So we want to know that theorem instead of doing all this work every time. So I did this part so that you get an understanding of where that's coming from. But I'm not going to do that again. I'm going to try to apply the theorem. So I'm doing the derivative of the integral from a constant to x of the square root of 1 plus e to the 5t dt. So it's up to me to know, well, this is a fundamental theorem question. I'm taking the derivative of an integral. Those are inverse operations of each other. And if I evaluated this, I'd be plugging x in for the t. So I get 1 plus e to the 5x, the square root of 1 plus e to the 5x. So it's a very straightforward theorem if you kind of recognize kind of what the question is and what the question's asking. Now, of course, it gets harder because we have to sometimes apply some different rules to this. Okay, so I'm gonna do this kind of the long way. So the way I did this example 1, the long way, and then we'll try to kind of just decide like, well, how can we do this the short way? Now, what's different about this example 3 is that the upper limit of integration isn't just an x. It's an x cubed plus x. And on these, the upper limit of integration was just an x. So basically, I could just substitute x in for the t. Okay, so let's think about this in terms of, let me think. I got to get my trying to think about how to go about doing this. Okay, so I'm going to do it the long way. Sorry about that. And then we'll kind of just look at the short way of doing this. So I'm going to not do the derivative here. And I'm just going to work on the integral. So to do the integral, I would find the antiderivative of t e to the t. Now, I'm not going to actually do that. I'm just going to write antiderivative because it's actually not an easy one to come up with. So we'll just say I found the antiderivative of t e to the t. And then I evaluated that from x cubed plus x to pi. So then to evaluate means, and I'm just going to do the antiderivative of t, so the antiderivative, and I'm going to put in my x cubed plus x times e to the x cubed plus x minus the antiderivative, whatever that happens to be, of pi e to the pi. Okay, so I'm evaluating that antiderivative at the x cubed plus x, and then I'm subtracting from that what that antiderivative is evaluated from pi e to the pi. All right, then I'm going to start taking the derivative of each of those parts. Well, the derivative of an antiderivative, right, those undo each other, just like we did in that last example. But because this here requires the chain rule, because my inside function, it's not just an x. So I do the derivative of the antiderivative of x cubed plus x, e to the x cubed plus x. But then I need to multiply that by the derivative of the inside function here, which is 3x squared plus 1. The derivative of the antiderivative of pi e to the pi becomes 0 because pi e to the pi is just a constant. There's no variables within that expression. So this is going to be our final answer. Now, we don't want to have to go through all this, and we especially don't want to do this when the antiderivative is something that's not easy. It's not easy to find the antiderivative of t e to the t. I mean, it's not e to the t, because that wouldn't make t e to the t show up. How do I get a t in front of there? Well, I might have to think about somehow using the product rule. So we want the shortcut of how to do this, how to get straight to the answer. Well, we still start by substituting that x cubed plus x in for the t's. We'll get that x cubed plus x, e to the x cubed plus x. And so in terms of the chain rule, that's like taking the derivative of the outside function. That's our outside function. But then I multiply by, because this upper limit isn't just an x, I multiply by the derivative of that upper limit, which is 3x squared plus 1. And notice that's the same thing we got there when we did it sort of this long and convoluted way. Okay? So let's try another one of those, recognizing that, hey, I'm taking the derivative of an integral. Okay, and those are inverses of each other, so those are going to cancel each other out. And I'm going to be substituting this in for the t. But because this upper limit isn't just an x, I'm going to be applying the chain rule. That's like the derivative of the inside function. So the derivative of the tangent of t squared is going to be the derivative of the integral of the tangent of t squared becomes the tangent of 5x minus 1 squared. But then that part right here is an inside function, so I'm going to multiply this by 5. And so that's my final answer on this one. That bottom part I don't need to worry about, because that bottom part's just a number, and when we take the derivative of constant, we get 0. Now, what happens if the variable is the lower limit of integration? When we look at the fundamental theorem, that lower limit is supposed to be the constant, and that upper limit is supposed to be the x or a function of x. Right? We substitute the x in, constant on the bottom, x is on the top. We substitute an x in, constant on the bottom, function of x on the top, so that applies the chain rule. Constant on the bottom, function of x on the top, chain rule. But now we've got x on the bottom, constant on the top. So we need to use one of our properties of integration. One of the properties of integration says that we can flip the limits of integration over if we negate the integral. That would bring the 5 down here and bring the x up here. I don't remember the name of that property. The order of integration, I think it was called. That's on the properties of integrals from our last section. Okay, once that x is on the top, now we can find the derivative. So we're going to do the derivative of this. So to do the derivative of an integral, we substitute x in for the t's into that function. So this becomes negative x sine of x. It doesn't require the chain rule because my upper limit of integration is not a function of x. Well, I mean, technically times 1 if you thought of it that way. And then the 5 I don't need to worry about because the derivative of a constant is 0. All right, our last one is an example of a problem where we have x's on both the bottom and the top. And so how do we do something like this sort of a setup? So this requires some of our properties of integration come into play. Okay, so because in order to apply the fundamental theorem, the lower number needs to be a constant and the upper needs to be x or a function of x. All right, so I'm going to work on this integral. So I'm going to do the integral from 3x to some constant, and my function would be 1 over 3 minus 2e to the t dt, plus the integral from a constant to x cubed of 1 over 3 minus 2e to the t dt. So what we're using there is the kind of additive, again, I don't know all the properties names, but it's like the additive property of integrals. So kind of graphically what I've done is, I don't know what this function looks like, but just roll with me on this. So say, that's my function, 1 over 3 minus 2e to the t. And we were going to integrate that from 3x to x cubed. Okay, we're trying to find the area under that curve from there to there. So what I've done is I've just picked some constant that's going to be somewhere in between those. There's some constant that falls in between there. And so what I've done here for this first integral is I said, okay, let's integrate. Let's find the area from here to here. And then I wrote a second integral to say, okay, let's find the area from here to here, which is the same as my original integral of the whole entire thing, which is this original guy, which would be the area from 3x all the way over to x cubed. So I've split it up that way so that each of these integrals involves a constant. Now, if we want to apply the fundamental theorem, I have to switch the limits of integration here because my constant needs to be down there at the bottom. I do that by putting a negative out in front. So that's another property of integrals. Now my second one was fine because I already have the constant on the bottom there. All right, now let's actually do the derivative of each of those parts. So this is like basically I'm distributing the derivative. So I'm doing the derivative of this first part, and then I'll do the derivative of the second part. So this first part, when I take the derivative, I basically just substitute 3x in for the t. But because 3x isn't just an x, I also multiply this by 3 because that's the derivative of 3x. So that's the chain rule. Plus, for the second integral, when I take its derivative, I substitute the x cubed in for the t. And then I multiply that by 3x squared because that's the derivative of x cubed. And I'm just going to leave it like that. I mean, there's no need for me to take any more time simplifying. I suppose if I just said I was going to leave it like that, but I'm going to keep going. I'm going to take that first fraction and make that negative 3 up at the top. The second fraction would have a 3x squared up at the top. And they would have common denominators of that 3 minus 2e to the... Oh, no, they don't. What am I talking about? Okay, I've just gone crazy here at the end of this video. I am going to leave it like that. And that's the last example for this video.